Hey, Algebra students. In this video, we are going to be learning about special systems of linear equations. These are systems of equations that have either no solutions, an infinite number of solutions, or just one solution. And what we're going to do is we're going to see what the graphs of these systems look like. This is something we worked with before, but we're going to make sure we understand what the graphs of these look like and why some systems of equations have infinitely many solutions, no solutions, or just one solution. All right, the special systems of equations we're going to be talking about in this lesson. First of all, we're going to talk about a type of system known as an inconsistent system. Inconsistent systems are equations that have no common solution. In other words, there's no xy coordinate pair that solves both systems of equations. Now, if you think about it, if you ever graph two lines from a system of equations and those two lines cross one another, the point at which they cross should be the solution to both equations, the xy coordinate that solves both equations. To have an inconsistent system of equations means that the graphs must never cross one another. And for that to happen, we must have graphs that are parallel lines. The only kind of graph on a two-dimensional coordinate plane that will never cross a different graph, the only way that that can ever happen is if the lines that make up those graphs, as long as we're talking about linear equations, the lines that make up those graphs have to be parallel to one another. A dependent system is another one of our special systems. A dependent system of equations has an infinite number of solutions, and the reason it has an infinite number of solutions is because the equations are actually the same equation. This would be like x plus y equals 2, 2x plus 2y equals 4. How did I get those graphs? Well, I just multiplied the first one times 2. And if I reduce it by dividing everything in the second equation by 2, I go back to the first equation. We're going to see what that looks like in some practice problems that we do later. But dependent systems of equations actually are the exact same equation on a graph, meaning that we're going to graph a line and then the other line is right on top of it. So every single ordered pair solves both equations. Next, we'll talk about a consistent system. A consistent system has at least one common solution, meaning that the lines have to intersect each other either at one point or at all points. Dependent systems, right up here, are consistent systems because the graphs of dependent systems intersect at every point, okay? And a consistent system could also be two graphs that just intersect at just one point as well. As long as they intersect somewhere, they're consistent. And then lastly, independent. Now, there's a little bit of debate as to what this one should be, what the definition is. In our book, it says that independent systems have exactly one solution. Other places will define independent systems simply as equations that have unique equations. You can't reduce an equation to the other one. So the big question is, do independent systems include parallel lines or do they exclude parallel lines? If they exclude parallel lines, then independent systems are going to have just one solution where two lines intersect each other. If they include parallel lines, then independent systems might have no solution. And the only difference, like if the only difference between the graphs is the y-intercept, if the slope is the same and the graphs are parallel to each other. Now let's look at some pictures and then we'll work some practice problems. This is an example of consistent and independent lines. Okay, notice that if two lines are consistent, um, they have to intersect at least one place. At least one place. So they could be the same equation if they're consistent. However, they're also independent, which means that they have unique equations. If they're consistent and independent, they have exactly one solution because they're going to intersect at a single point. The only way they wouldn't intersect at a single point is if they were parallel to each other, but parallel equations are not consistent because they have no intersection. So, This would be a consistent and independent example. Next, we're going to look at consistent and dependent. If we have two graphed lines that are right on top of each other, those would be consistent and dependent because the graphs are actually of the same line and they intersect at every point. And then lastly, inconsistent equations. And here's where the debate comes in. Are these just inconsistent, or are they inconsistent and independent because they're different equations? But regardless, inconsistent equations have no solution because the lines are parallel. The lines will never intersect one another. They'll just keep going in both directions. We can tell from the equation because both of these lines would have the same slope. They'll have different y-intercepts, but the same slope. All right, let's work some practice problems. We need to solve letters A and B. So let's start with that. Letter A. And our equation is, let's see, if we solve this, we're going to solve this through substitution. And if I know that y equals this and y equals this, I can set these equal to each other because y equals the same, y equals whatever this expression is, y equals whatever this expression is. Because they're equal, I can just say 1 half x plus 1 half equals 1 half x plus 7. And you probably can pick out what the problem is going to be with this. I'm going to subtract 1 half x from both sides. What am I going to get? Well, if I subtract 1 half x from both sides, it goes away, and I get 1 half equals 7. Well, that is an incorrect statement. So this one has, whenever I get a number that is equal, it says it's equal. The equation says it's equal to another number that it's obviously not equal to. The answer is that there is no solution. Hey, if I would have looked at these lines in slope-intercept form here, immediately I would have noticed these are parallel lines. They have the same slope, different y-intercepts. That means because they're different lines, but they're parallel, they're going to have no solution. I could have noted that just right from the beginning by noting they were parallel lines. All right, letter B. X plus y equals 10. Negative x minus y equals negative 10. Now, there's two ways for me to solve this. One way is for me to use substitution or elimination. Boy, if I used elimination with these, I'd eliminate both x and y at the same time. What I would do is maybe use substitution. So I'd say I'd first of all subtract y from both sides on the top. X equals, let's see, what is it? Y. Let's see, 10 minus y if I subtract y from both sides. And then the next equation is, well, let's see. Actually, for the next equation, now that I know that x equals 10 minus y, I'm going to plug in 10 minus y for x. So negative, open parenthesis, x is 10 minus y. So I'm going to plug in 10 minus y. Minus y equals negative 10. Okay, so when I distribute that negative, it's going to become negative 10 plus y minus y equals negative 10. Now, notice I have plus y and minus y on the same side of this equation. I'm going to simplify by getting rid of plus y minus y. That's just 0. I get negative 10 equals negative 10. Anytime I get a number equal to itself, that proves that anything is a solution. So the solution is there are infinitely many solutions for this one. All right, letter C. Determine if the system of equations is consistent and independent, consistent and dependent, or inconsistent. So I have to figure out whether they intersect at one point, whether they intersect at every point because it's the same equation, or whether there is no solution. So for this one, let's see. I'm just going to look at this one by inspection and note that 4y equals 4x plus 4 is the same equation as negative 4y equals negative 4x minus 4 because this is just multiplied by negative 1. So by inspection, I can say that these ones are dependent and consistent because they're parallel. They're the same line. They're the same line that makes them dependent. And if they're dependent, they're also consistent. Okay. Letter D. Negative 2x plus y equals 3. Y equals negative x minus 2. This one's not quite obvious. So what I'm going to do is I'm going to plug in, because I know that y equals negative x minus 2. I'm going to plug that in for y. 2x plus negative x minus 2 equals 3. Okay, so let's solve this. I'm going to combine like terms. It's going to be negative 3x minus 2 equals 3. Negative 3x equals 5. And then x equals negative 5 over 3. And then I can figure out what y equals. So if I go back to my equation, I know that y equals negative x minus 2. So I'm just going to write that y equals negative x minus 2. If x is negative 5 thirds, that means that y equals negative 5 thirds. So that's 5 thirds minus 2. Let's think about that for a second. So 5 thirds is 1 and 2 thirds. 1 and 2 thirds minus 2 minus 6 thirds. So this is 5 thirds minus 6 thirds is negative 1 third. Hey, there is one solution for x, y for this system of equations. So that means that this system of equations is with exactly one solution, independent and consistent. So I'm just going to write that down. Independent and consistent. All right, there we go. So one more question to answer. Let's see if we can get this all on one line here. Just barely missed it. That's okay. All right, one more equation or one more problem. Letter E. An emergency road service company offers different plans to its customers. Plan X offers service calls of $22 each. Plan Y offers a lower rate per month with an additional charge of $12 for each service call. How many service calls would it take for Plan Y to cost the same as Plan X? Explain. Okay, so when I read this, the thing that it doesn't say is that this is in 1 month. You have to kind of infer that from what it says. So, how much is it going to cost for Plan Y to cost the same as Plan X in a month? So you don't have to worry about like multiplying $40 per month times the number of months, because this is just in 1 month. How many service calls is it going to take for these to be the same? So the total cost is going to be y. Y with plan X equals 22 times the number of service calls. We'll just use X for the number of service calls. You don't pay an upfront fee per month. With the other plan, you need to pay $40 per month. So the total cost in the second plan is going to be $40 plus $12 per service call. So you get a discount per service, but you have to pay $40 up front. So the question is, how many service calls does it take for plan Y to cost the same as plan X? Well, since they both equal Y, I can set them equal to each other. 22x equals 40 plus 12x. I'm going to subtract 12x from both sides. That gives me 10x equals 40. Let me just make sure I did that right. Okay. And then I'm going to divide both sides by 10. X, the number of service calls, equals 4. Now let's just make sure that this makes sense. If I do 4 service calls on plan A, that's going to give me a total cost of 22 times 4. That's going to be $88. Okay. If I do the same thing on plan B, y equals 40 plus 12 times 4. 12 times 4 is 48. 48 plus 40, well, $88. So that makes sense. So the question is, how many service calls? 4 service calls, because at 4 service calls, it cost me $88 in plan X, and $88 on plan Y. That's how and notice that this set of equations was consistent and independent, so there is just one solution. It didn't cost the same amount no matter what. It only costs the same amount for 4 service calls. That's how you do these sorts of problems. Make sure you do numbers 1 through 34 next time.